Whether it's a massive refinery processing crude oil, a bustling petrochemical plant manufacturing polymers and chemicals, or a high-capacity power station generating electricity for cities, heat exchangers are absolutely everywhere in these critical industries, handling the efficient transfer of thermal energy between fluids on a massive scale. But have you ever stopped to wonder how skilled engineers ensure that these enormous pieces of equipment, weighing hundreds of tons and operating under extreme pressures and temperatures, remain safe, highly reliable over decades of service, and standardized globally across manufacturers and borders? Today, we're diving deep into API 660, the world-renowned standard developed by the American Petroleum Institute specifically for shell and tube heat exchangers predominantly used in the petroleum refining and natural gas processing, as well as the broader chemical processing industries worldwide. Make sure to stay with us all the way till the end, because I'll be covering essential definitions straight from the standard, practical real-world examples from refineries and plants, and key design insights that every engineer, from fresh graduates to seasoned veterans, absolutely must know to succeed in their projects. You can think of API 660 as the comprehensive rulebook or blueprint that guarantees every shell and tube heat exchanger, whether it's a compact small cooler for auxiliary services or a gigantic refinery condenser handling thousands of tons of vapor per hour, is engineered, built, and tested safely and with perfect consistency, regardless of which reputable manufacturer anywhere in the world is producing it. For instance, if India's ONGC procures a critical heat exchanger from domestic giant L&T, and at the same time Reliance Industries orders an identical unit from international leader Alfa Laval, API 660 ensures both units adhere strictly to the exact same minimum design, fabrication, and testing criteria, promoting interoperability and trust. In the high-stakes environment of a petroleum refinery, where operations run 24/7, a single heat exchanger failure can lead to production shutdowns costing tens of millions of dollars in lost revenue, environmental releases, or even serious safety hazards endangering personnel and facilities. That's why API 660 is meticulously designed to prevent catastrophic problems such as tube rupture from excessive pressure differentials, shell cracking due to fatigue over cyclic operations, thermal stress failures from uneven expansion, and many more vulnerabilities. Beyond those, it also rigorously prevents vibration-induced tube damage from flow instabilities, incorrect material selection leading to rapid corrosion, and subpar fabrication quality that could compromise structural integrity under operational loads. To visualize the basics, picture this simple graphic on screen: the robust shell enclosing a bundle of precisely arranged tubes, through which process fluids flow in carefully controlled paths, either countercurrent or co-current, to maximize heat transfer efficiency. Consider a real cautionary example: a gas cooler in a petrochemical plant designed without the mandatory API 660 vibration analysis could experience severe tube bundle failure, with tubes cracking and leaking within just 6 months of commissioning, leading to costly repairs and downtime. API 660 meticulously covers every single critical part and assembly of a shell and tube heat exchanger, from the outermost components to the innermost details. Let's systematically break them all down one by one for clarity. Starting with the shell, which forms the large outer cylindrical pressure vessel body that contains and carries one of the process fluids safely, and it must be precisely designed and stress-analyzed in full accordance with the stringent requirements of ASME Section 8 Division 1 Pressure Vessel Code. Next, the tubes themselves are the small-diameter seamless or welded pipes, typically 3/4 inch to 1 inch OD, meticulously arranged in bundles to facilitate the primary heat transfer between the hot and cold fluids flowing inside and outside them. The tube sheet serves as a heavy-duty gasket-like plate that securely holds all the tubes in their precise positions, preventing leaks and movement, while the channel head or bonnet enclosure covers and directs flow on the tube side, often with partitions for multi-pass configurations. Inside the shell, segmental baffles are strategically placed to direct and turbulate the shell side fluid flow, dramatically improving overall heat transfer coefficients, and crucially reducing flow-induced vibrations that could otherwise damage the tube bundle over time. Take a classic 1-to-1 pass exchanger configuration as an example. The baffles must be spaced according to strict API 660 limits, typically no closer than 1/5 of the shell ID, to minimize vortex shedding frequencies that resonate with natural tube frequencies and cause damaging vibrations. One of the foundational definitions in API 660 is design pressure, which represents the absolute maximum pressure each side of the exchanger, the shell side and the tube side, must be engineered to safely withstand continuously without deformation or rupture. Similarly, design temperature is defined as the highest metal temperature that any part of the exchanger is expected to reach during normal steady-state operations or occasional upsets, dictating material selection and expansion allowances. Corrosion allowance, abbreviated as CA, is the additional metal thickness deliberately incorporated into the shell, tubes, and heads to compensate for gradual material loss from corrosion or erosion over the equipment's long service life, with API 660 typically specifying values between 1.5 mm and 3 mm depending on the corrosive service. Fouling resistance quantifies the anticipated thermal resistance to heat transfer arising from the buildup of deposits, scales, or biological growth on heat transfer surfaces, and API 660 mandates using fixed, service-specific fouling factors published in standards like TEMA for conservative designs. Furthermore, API 660 directly references and incorporates TEMA mechanical standards designations, such as ES for floating head with split backing ring, BU for U-tube bundle, BM for fixed tube sheet with bonnet, and many others to precisely specify front head, shell, and rear head types. For a concrete example, an exchanger designated type BM breaks down as follows. B stands for the removable bonnet on the tube side, E indicates a single-pass E-shell flow path, and M denotes the fixed tube sheet construction at both ends for simpler but rigid designs. Tube pitch, the critical center-to-center distance between adjacent tubes in the bundle, is governed by API 660, which recommends a minimum of 1.25 times the tube outer diameter to ensure adequate flow area, cleanability, and structural ligament strength between holes. Under mechanical design provisions, the required shell thickness is calculated rigorously per ASME, a formula accounting for pressure, diameter, and corrosion, while tube sheet thickness follows specialized API 660 appendices combined with ASME ligament efficiency methods. Additionally, mechanical design encompasses clear bundle entrance/removal clearances for maintenance and nozzle reinforcement calculations per API 660 geometry rules plus SME 8UG 37 to handle localized stresses without supplemental pads where possible. In challenging crude oil service applications, for instance, the tube sheet must be sufficiently thick to endure differential thermal expansion stresses arising from hot 150 degrees Celsius crude oil on one side versus ambient 40 degrees Celsius cooling water on the other, preventing warping or leaks. Tube layout rules in API 660 strictly specify allowable patterns like 30-degree triangular or rotated square pitch arrangements, with minimum ligament widths between tube holes for strength and baffle spacing always greater than or equal to 1/5 of the shell inside diameter. Moreover, shell side bypass lanes around the outer tube rows must be sealed or sealed with dimensions controlled per API 660 to prevent fluid short-circuiting that bypasses the tube bundle and induces excessive vibrations. On materials, API 660 approves and lists qualified options such as SA 516GR70 carbon steel for general moderate temperature services, 304/316 stainless steels for corrosive environments, low alloy steels like 1.25 CR, 0.5 MO for high temperatures, duplex stainless for chloride pitting resistance, and Admiralty brass specifically for non-chloride cooling water duties. Thermal design validation under API 660 requires the proposed geometry to precisely meet the specified heat duty in terms of megawatts or M2 per hour, stay within allowable shell and tube side pressure drops, typically under 10 to 20 psi, incorporate fouling allowances, and achieve minimum temperature approach differences per service norms. Fabrication demands qualified welding procedure specifications complete with procedure qualification records. Execution only by API-certified welders, and post-weld heat treatment applied as mandatory for certain P numbers and thicknesses to relieve residual stresses. For quality assurance, API 660 mandates 100% radiographic examination of critical welds, liquid penetrant testing on full penetration welds and tube-to-tubesheet joints, plus a final hydrostatic shell test at 1.3 times the design pressure and pneumatic channel test where applicable. Precision tolerance requirements detailed in API 660 include tube sheet hole diameter tolerances of plus 0.001/-0.000 inches for rolling, maximum bundle projection beyond the shell, tube straightness not exceeding 1.5 millimeters over 1 meter length, and flange face alignment within 0.25 millimeters parallelism. During tube-to-tubesheet jointing, tube expansion must strictly adhere to API 660 prescribed torque values for strength-welded joints or explosive/rolling expansion limits to achieve leak-tight seals without excessive tube wall thinning below minimum schedule. As part of mandatory vendor data submission, the manufacturer must furnish complete mechanical design calculations including stress reports, detailed thermal design rating sheets with performance curves, and fully qualified welding procedures with supporting PQR data. They must also deliver comprehensive NDT examination records with radiographs and reports, material test certificates or mill certificates tracing to heat numbers, and as-built engineering drawings such as general arrangement, individual fabrication details, and precise nozzle schedules. In a typical crude preheater application, where high-temperature crude oil flows through the tube side and condensing hot vapors occupy the shell side, API 660's material selection clauses ensure alloys are chosen to resist accelerated corrosion from sulfur compounds and mitigate thermal fatigue from temperature cycling. For a cooling water exchanger handling aggressive seawater on the tube side, API 660 explicitly requires proven pitting-resistant alloys like 90 to 10 CUNI or super duplex stainless steels to prevent localized pitting corrosion that could perforate tubes prematurely. In a steam surface condenser setup, with condensing steam on the expansive shell side and cooling condensate or water on the tube side, API 660's stringent vibration prediction and damping rules are essential to avert tube failures induced by high-velocity steam crossflow. So, that concludes our thorough, section-by-section breakdown of API 660, the definitive shell and tube heat exchanger standard that sets the global benchmark for quality and safety. Whether you're a university student studying mechanical engineering, a design engineer specifying equipment for new projects, or a plant maintenance professional troubleshooting in-service units, mastering API 660 empowers you to deliver safer, more reliable, and universally accepted heat exchangers. As a quick recap on screen, we've covered all the essentials: heat definitions with specifics, practical real-world examples from industry, comprehensive design rules for mechanical and thermal aspects, fabrication best practices, rigorous testing protocols, and complete documentation requirements. If you're eager for more deep dives, let us know in the comments below if you want dedicated videos on related standards like API 650 for storage tanks, API 661 for air coolers, or the full TEMA standard suite. Don't forget to hit that like button if this was valuable, share it with your engineering colleagues and teams, and subscribe to the channel for a steady stream of more simple GAN engineering content design just for professionals like you.